Hello students, so this is chapter 2 or 10.2, okay, which what we are going to do is to learn about what effects does the transfer of heat energy have on an object. Okay, this is something that is quite relevant in many ways. Okay, so let's start with the main understanding first. Okay, what you see here is that first the transfer of energy can cause objects or substance to expand or contract. When you think of expansion and contraction, will you be thinking of size or volume? Right? If you're thinking of that, then you're on the right track, okay? So when anything gains heat, when it's heated, of course, it expands, right? Expand here, of course, that means the volume increases. Reverse, when a substance or anything that is being cooled, it loses heat, right? Releases heat, and what happens to the substance? It will contract, right? And contraction only means the volume decreases. Okay, so the next point we should see here is quite a main point. Take note. When you look at expansion and contraction, it will occur in all type of states, meaning solid, liquid, and gaseous state. Okay, so any substance, whether they're in solid, liquid, gas state, expansion and contraction will occur once there's heat transfer taking place. Okay, and I think the example below will show you. Okay, in fact, the two examples below is something that we must be very careful about, right? Because if we don't handle this expansion in particularly properly in the two examples, it will be very, very disaster. There will be a lot of accident, which of course is not going to take place because engineers has already taken care of the issue. Okay, so let's go into the two examples now. Okay, the first example, I think most of you will know what it is. It's about railway track, right? Or even our MRT track is in this issue. Okay, so let's read. So when it's a hot weather, which Singapore is, of course, okay, tropical. So what happened to the metal that we use to make the railway track? It will gain heat, right? And then it will expand. Or in this case, while we say volume expand, volume increase when it expand, we also are thinking of volume involve length. Okay, you know the railway track is long, not so much of the width and the height, but in terms of the length. So the length will expand, or the length will get longer, and that's where the problem is, isn't it? So when the length is expanded long, and if the track is one piece of continuous metal, what do you see in the picture? Will the track still be straight as the metal expanded and get longer? The term there that we normally use is the track buckle. Okay, buckle, B-U-C-K-L-E. Buckle means it will not go straight anymore. And of course, if the train goes through the track that is not straight now, the accident will occur and life will be in danger. Okay, so how would then this problem be solved? You're not going to lie long, continuous long railway track. So the solution is here, right? So over certain length of the track, they will have a joint. Okay, we call it the expansion gap, where actually in between two tracks there is a gap, which then obviously this gap allows for the expansion of the track. So the track can get longer in between the gap, and then that allows the track to be still straight. Okay, so all this has been designed for already. So we will not have any issue taking the MRT train or any train in the world, okay, especially in a hot country like us, like ours. Okay, the next example, you may have observed this on the road, especially when you're looking at bridges, okay. Same thing, bridges, okay. So solid, right? Bridges are all solid. So in a hot day, bridges solid expand more, okay, expand more. So if this expansion involves the length getting longer, isn't it not dangerous if the bridge has no way to expand its length? Okay, same thing, when the day is cold or the weather is cold, the bridge will contract, okay? It loses heat and you contract. So how would they, in a way similar to the railway track, when this happen, expansion and contraction happen, it will not cause damage to the bridge, right? You don't want any bridge to start to have so-called damages due to the expansion contraction. So the solution in this case is also about putting in some joint. In this case, it's called the expansion joint, okay, along the span of the bridge. So if you look carefully as you travel in a vehicle, as you cross a bridge, you may see this metal strip at certain part of the bridge, along the bridge. Okay, actually this is the expansion joint. All right. So this is to take care of expansion, just like in the railway track, right? So it actually gives you some movement, okay, when the bridge expanded, okay. So this is allowing it to do so. But in the case of contraction, the bridge actually will also get shortened, right? So another way to solve this is not the expansion joint issue, is when they use rulers. Okay, these rulers are designed, which you actually can't see because at the support below the bridge. Okay, actually the ruler is part of the support. What happens will then, when the bridge need to move, especially during contraction, these rulers will then allow the bridge to, okay, make that movement, right, to allow it to move, okay, whether in expansion or contraction. So this will not affect the design of the bridge. It will not cause damage to the bridge. So in this case, with this kind of design, we have solved the problem or the issue of expansion and contraction, especially in these two scenarios. Okay. Okay, this is slide number 2 of the chapter on 10.2, and the first slide we have discussed about the expansion in solids. For these slides is expansion in liquids on the first part, and the expansion and contraction of in liquids and gases. Okay, let's start with the first part. Okay, as you can see in the diagram here, okay, and in the first paragraph here, oceans absorb more than 90% of heat energy. Okay, liquid can absorb heat too. Okay, and in our case, we are surrounded, okay, by seas and ocean, and heat from the Earth atmosphere can be transferred into the water, okay, in the sea water. And of course, this is important, as you know, there are marine life that needs suitable temperature, okay, and this heat that the water absorbs is to maintain this temperature, okay. But now the issue is this: what happens if the oceans continue to absorb more and more heat, resulting to an overheating? How would this affect the marine life? Okay, that's one case. Plus, you also want to look at what we are illustrating below in this box 1 and 2. So as you know, when water absorbs more heat, okay, it will expand, right now. It will expand. And why is this important? Because as you can see, or as you know more recently, that we are talking about climate change, that is commonly linked to global warming, right? And what does this mean? Means that atmosphere has more heat trapped, and with that, the ocean will also be absorbing more heat. Okay, and when the ocean, in this case the seawater, absorb more heat, it will expand. And what's the consequence? Or what's the result of this expansion? There's no need to think too much. The sea level will increase. So when the sea level increase, is it a good thing or a bad thing? Especially in a country like Singapore, where we are surrounded by the sea. Okay? So when the sea level increases, what happens to the coastal part? The coast will be submerged, right now. The sea level will get higher, the land or the coastal land will get washed away, will be underwater. And other than that, there will be coastal erosion too. Means those areas beside the sea cannot be used or you'll be damaged. Okay, so that's the first part here in the slide. So the next part we're looking at expansion and contraction in liquids and gases, right? You look at the diagram on the right, you will see big metal pipes. I don't think you see this commonly anywhere. Okay, this is only found mainly in industry. Okay, and like I said earlier on, metal, in this case metal pipes, they expand and contract, right? I mean metal, right? You know, they actually expand more and contract even more. Okay, but in this case, what is inside the metal pipe? They carry steam and hot water, right? They carry steam and hot water. Okay, the outside temperature is lower than the high temperature inside. So there will be a lot of expansion and contraction. And what does it mean? This excess expansion or a lot of expansion and contraction is actually quite damaging, right, for the pipe. So the engineer, in order to ensure that the pipes are not damaged or not break, they actually design the metal pipes with bends, which allow this contraction and expansion to take place safely. Okay, so this is how expansion and contraction is being taken care of in the pipes. Okay, I hope these two parts here is not difficult for you to understand. See you next time. In this slide, we'll be looking at the applications of expansion and contraction due to the heat transfer into our daily life. Okay, so right at the beginning here, just a quick overview. We'll be looking at 4 applications. Okay, on this first slide here, you see that it's about how we can use expansion, right, due to heat transfer in metal to open a jar. Okay, I know we all sometimes, or your parents sometimes find it very difficult to unscrew a tight jar, right? So this is actually quite useful. So as you can see in the picture below here, you have some hot water in a bowl and put the lid into the hot water. Okay, of course the jar with the lid in the hot water, okay, and wait for a while. Okay, as you know, glass does not expand as much as the metal lid. So after the metal lid has absorbed enough heat from the hot water, it will expand more than the glass. So after which you take it out, and then you find very easy to unscrew the tight lid. Okay, so of course I'm not asking you to go back and try, but one of these days, if your parents have this problem, instead of using brute strength, you may want to just suggest to them. Okay, so this is the first application. This is another application of expansion and contraction due to heat transfer. Before we talk into the actual application, okay, this is what you're seeing now is a bimetallic strip. Okay, the word bi means make up of two metals. Okay, metals. And what is important here is that the two metals, they have different expansion and contraction, okay, due to any change in temperature. Okay, take note of that. So the example here that we see in this bimetallic strip is made of brass and steel. Okay, and see from here. Right. So if you read this next sentence, brass expand and contracts more than steel. Okay, take note of that. Brass expand and contract more than steel. Okay, of course, then they are being joined together. Okay, sometimes by welding, sometimes by riveting. But this part not important. Okay, so if you look at the diagram carefully, okay, so this is heating, this one is cooling. So if you say brass expand more than steel, can you see that this part, which is the brass, has actually expanded longer because it has more expansion. Okay, if you look below, which is where the steel is, it is not expanded as long as the brass. So you have this shape when you are looking at heating, when this bimetallic strip is being heated. While on the below diagram, if now the bimetallic strip is being cooled, okay, same thing, the brass will contract more, right? And because it contract more, it become shorter, okay, than the steel. So this is how then it will bend in this manner. Okay, take note of the shape. Okay, but important, brass expand and contract more than steel. Okay, this is a very important key point. Okay, so once you know how a bimetallic strip, in this case using brass and steel, how are they going to, what's going to happen to them or to this strip when there's heating or when there's cooling due to the heat transfer. We then think about where is it being used. Okay, so we can read here. It's actually used in places where you don't really see them. Okay, it's inside the devices. Okay, so one of them would be your thermostat. The other one is actually a bimetallic thermometer. Okay, of course earlier on we didn't mention that there's such a thermometer, but now you know. Okay, so what is a thermostat? Okay, in this case, a thermostat is a device that is used to keep the temperature of appliances constant. That means it is to help to control and maintain constant temperature. So where do you find thermostat? Or where will you find devices or appliances that need temperature to be kept constant? Of course, I think it's something that you should be familiar with. Okay, one example would be your refrigerator, right? Also ovens, and then your electric irons. Okay, there are other example too, but these three I think should be most common to all of us. Okay, so a thermostat inside these appliances, okay, by you setting the temperature, you actually setting this control in the thermostat so that the temperature in the refrigerator, the ovens and the iron will not go below or higher. Okay, you'll be kept at the constant temperature that you want to keep it at. Okay, so the next slide we will then look at more details of what happened. Okay, how the bimetallic strip works. Okay, see you next slide. Hello students. So if you have still not very sure on how a bimetallic strip works, please go back to the earlier video. Okay, but for now, this is the slide that will explain how a bimetallic strip works in an electric iron. Okay, so it is quite heavy, so you must try to pay attention and then go back to the earlier slide, okay, on the how to explain the how the bimetallic strip work. Okay, so all of us uses electric iron at home, right? So when you uses electric iron, you need to on the electricity, and then the iron will heat up, right? Then, of course, there's a control knob that you can set, which is where the bimetallic strip is inside. Okay, that's what you can see in this diagram. So you really can't tell how it looks like. Okay, this is the illustration only. Okay, so when you set the temperature to the temperature that you want based on the type of clothing that you're ironing, okay, the iron, once it reaches the temperature, okay, that you set, it will then switches off and cool down. I think it's obvious, right? You don't want the iron to continue to be getting hotter and hotter, because then it may burn your clothing. Okay, so this is where this thermoset using the bimetallic strip helps to control the temperature. Okay, now how this all works, we will need to then look through the explanation given in 1, 2, and 3, step by step, of course together with the diagram, the two diagrams below. Okay, so let's start. Okay, so I hope you are still clear-minded. Go. The first one, of course, like I said earlier on, the knot is the one that you turn to set to what type of clothing that you're ironing, because it will then let the iron know, or let the bimetallic strip or the thermostat knows how much temperature will be needed. Okay, so this is the first part. Okay, now what you see in point number 2, or the second box, is that the iron, inside the iron, the bimetallic strip before the iron is switched on is actually straight. Okay, it has not expanded, or it has not bent, okay, at the beginning. Okay, so this one is just to highlight this point. So as you switch on, electricity cause heating to occur, and then step 3 or point 3 will then explain to you. Okay, so let's look through it in a bit more detail. So as heat is being supplied, as the iron is switched on, the bimetallic strip, as it absorbs, or as heat is transferred into the bimetallic strip, it will expand. Okay, remember the bimetallic strip, also shown in the illustration, is actually made of steel and brass. Brass is on top and steel is at the bottom. Okay, this arrangement is important to understand how it will switch off the iron when the right temperature is reached. Okay, so again, here it repeats, the brass strip expands more than the steel strip. Okay, so heating is taking place, the iron is getting hotter. So as the bimetallic strip expand, the brass expand more, the steel expand less. So what do you notice? What happened to the bimetallic strip now? When it first started, it was straight, right? So when it's expanded, what happened to the strip? It will bend down, right? It will bend downwards. And what do you notice? When it bends downwards, there will be it will open the contact. What it means here means now the circuit will be open. Electricity will not flow anymore, okay, into the heater, into the iron. In other words, the paramagnetic strip after it's expanded will switch off the iron. Okay, will switch off the iron. Okay, although electricity is still being left on, okay, the switch is still left on, but this acts as a control to off the iron. Of course, the last part is that you don't want the iron to actually stop ironing, right? So when the bimetallic strip cools down, what happened to the bending of the bimetallic strip? It will contract, right? So it will contract, right? So then the strip will do what? Will contract and it will go back straight. It will return back upward and then it will touch the contact again. Okay, so this part closes the metallic strip with the circuit again. Then the whole iron will be heated up again. So this will continue in this way as long as you are ironing. Until you finish, of course, then you off the iron. Okay, I hope this explains a bit better. Well, this is the final application involving expansion and contraction. Okay, in this case, it's a hot air balloon. Maybe some of you are lucky enough to have gone overseas and taken a ride on this. Okay, but of course, all of us know what's a hot air balloon. So what really happened? Okay, right. If you read the explanation here, right. So when air in the hot air balloon is heated, like all metal, matter, the volume increases, right? Okay, the volume increases, but what you understand is that the mass of the air remain constant, which means all the air particles inside the balloon does not change. Okay, only the volume has increased. Okay, expanded. Okay, so when this happens, still remember the formula or the chapter the topic of density. So what's the meaning of density or the formula? Mass over volume, right? So based on what I said earlier on, if mass is constant and now volume has increased, so the effect on density will be density will decrease, right? That's why this is how you use the understanding of density, okay, which you actually learned in chapter 2. Okay, hopefully this is not forgotten. So as you can see, when the density of the hot air, okay, has decreased, it means the air now is less dense, right? And what happened to any substance that has lesser density? The air will rise up, right? Less dense hot air rises. And because of that, it is able to float the hot air balloon. Okay, the part below 1 and 2 just explain in further detail before and after when the air is being heated up. But what is more important before I end this slide, right, for this chapter 10.2? Can you see the question here? Can you see the question there? how do we make the hot air balloon come down? Okay, so you can think reverse. As for the case of from a deflated balloon, how did I make it due to heat expansion of the air to cause the balloon to rise up? So now I want to make the hot air balloon come back down. Okay, don't forget, this is expansion. Now for this question, the idea will be about contraction. Okay, still need to talk about density. Okay, by this point, I'll let you think about it. Okay, bye.